thought you were going to say beautiful topic or something. But yeah, that too. Yeah, okay, great. All right, so this is part 2 of first-class continuations. I'm going to begin with a like 2-slide recap of what we talked about yesterday morning, since there were a couple of intervening talks and drinks. And then we'll get on to how to implement first-class continuations by source-to-source translation. Okay, so just 2 slides. So I think the thing to understand before you understand continuations is the concept of an active expression, which in a program is, you can think of it as intuitively as the smallest part of the program that you're going to evaluate next, right? So if this is your program, so log 2 plus 3 times 4 followed by log high, then the active expression is 3 times 4, because that's the first thing that we're going to do. So the continuation of an active expression is just everything else, excluding the active expression. So since that's the active expression, the continuation is everything else, and everything else is a program with a hole in it, and the way that I've been writing it is as, I've been writing the hole as a box, so that's the continuation. Okay, and the sort of important thing to note is that this is just like fundamental to computation. All programming languages have continuations. Not all programming languages have first-class continuations. Okay, so in programming languages with first-class continuations, there's some sort of primitive operator that can turn the continuation into a value. This is called capturing your current continuation. So the operator that I introduced is one that's called control. It's a unary operator. It takes a sort of a unary function as an argument f, and what it does is that it turns its own continuation into a value and passes that as the argument to the function f, and it runs that function in the empty continuation. So I think the simplest example of what you can do with this is fudge synchronous blocking operations in the browser. So we saw that, so I gave this pure JavaScript example where if you wanted to write a really simple program that does 3, 2, 1 liftoff with a 1-second pause in between each one, you needed like 3 different auxiliary functions to pull that off, because that's how JavaScript is. There is no sleep function. But you can simulate a sleep function using control. It's really straightforward. All that we do is capture the current continuation. So when we hit sleep, that sort of creates a continuation that has everything else in it. And then in the sleeper, we start an asynchronous timer, and after n milliseconds, so set timeout is a JavaScript primitive, and after n milliseconds, it's going to call this function. This function is a continuation function, so it's just going to resume the program. Then we get to the next sleep. The continuation we capture is this. Same thing occurs. All right, so these are, so by the way, as yesterday, interrupt me if you have questions about anything. The best way to understand code is to, when someone says, here's a piece of code that does this, the best way to understand it is try to change it into, turn x into x prime and see how it breaks, if it breaks. So again, as we did yesterday, ask me to change things if it'll help you understand things. I just want to give one more example of continuations that's not something that I covered yesterday that I think will be informative. And then we'll get on to implementing continuations. Okay, so this, what happened to my run button? Oh, okay, so apparently, one sec, let me refresh this page. Okay, there we go. Resizing in JavaScript is extremely challenging. For me at least. Okay, so I'll get to the implementation of this stuff later. This is how I'm using it. So what I've implemented here is an operator called choose that implements non-deterministic choice. And so the idea is that choose is going to return any one of these values. And when you call choose when you call choose in a function passed to this other function that I've implemented called driver, what you get is all possible outcomes. So what's happening here is that we're here. Let me comment this out first. So what's happening here is we're calling we're getting a number between 1 and 6 inclusive. We're getting another number between 1 and 6 inclusive, adding them all up, calling them in the driver, printing the result, and what the driver prints is an array of all possible outcomes. So if you run that, what is the, oh, sorry, this is, let me get rid of this line, because it's just silly. And that's what that prints. That's, the coloring is stupid, but it's sort of all possible combinations of x and y. So you can think of this as like, you take two die, you roll them, this shows you all possible combination, all possible sums that you can get. So the other thing that you can do here, let me uncomment this line, is you can say, well, if x plus y mod 2 is not equal to 0, we'll just blow up with an exception. And so when that happens, this is not going to sort of kill the program. Instead, it's going to rule out that outcome. So this, if you run this program, will show you all possible ways of getting even numbers out. Now, this is the sort of the beginning of something called probabilistic programming. So one of the things that we can do is it doesn't take too much work to start returning not just outcomes, but also probabilities. And then what we can do is we can, yes?
Are there numbers on the right-hand side?
What? You mean off the screen?
No, on the right-hand. There are blue things.
Oh, yeah. Oh, you guys, I'm sorry. Yeah.
I can't see it.
Yeah. Yeah, there's numbers. Sorry.
No.
Yeah, so, yeah.
Something like that?
I'm not going to recompile this editor at this point, but yeah.
That would be cool. So that's fine.
Yeah, but sorry. So this is like the only time I'm going to spend in this editor. But if you have color issues or like zooming issues, because I'm going to show some graphs towards the end, just ask me and I'll zoom in.
Many issues, thank you.
You have many issues. Great. Okay, I'll help you as much as I can. Yeah. Okay. So these are, what was this? So this is all possible ways of getting even numbers out of two rolls of a die. So let's, any questions on this at this point? Okay, so let's briefly look at the implementation, which uses continuations. Oh, I really wish I hadn't done that. Is this readable? Is this readable at the back? Jan, can you guys see this?
Yeah, vaguely.
Vaguely, okay.
Turning off the lights, see if that helps any. Keep going.
All right, okay, I'll keep going. Okay, so the basic idea is this. What the choose function does, so remember, choose receives an array of arguments. A little JavaScript tidbit, you can call a function with multiple arguments, and when you do, those arguments go into an array-like object called arguments. So I'm turning it into an actual array. And what choose does is this. It captures the current continuation. And let's ignore the for loop for a moment. What it does is it immediately returns to the current continuation the first outcome. So if you say like choose 1, 2, it's going to immediately return 1. But then what we're doing in this for loop is we're pushing on a number of thunks. So the important part is this. We're pushing into the for loop a number of thunks where each thunk applies the continuation k to each of the other values. So if you write choose 1, 2, 3, we're going to immediately return 1. Okay. Can you see me? Yeah. All right, great. So we're going to immediately return 1, and there'll be two functions pushed onto the array, which when applied will return 2, which will return 3, and so on. So that's sort of basically it. And then the driver function is just about like managing that. What the driver does is we have this array of results. Let's ignore the try. What the try catch does is when you throw something, it lets you ignore that outcome. So all we do is we call the body and push the first outcome onto the results array. And then if there's additional results, if there's additional continuations in that array of continuations, we pop the first one off and simply call it. Okay, and that's all that's necessary, because what's going to happen is that when we re-invoke that other continuation, we end up sort of returning back here. So we saw this, so like I fudged the while loop yesterday, which was sort of pointless because, you know, we have while loops. There's no need to like re-implement while loops. But this is the same concept again. So the first time we return here. When we re-invoke that function down at the bottom, we again return here. So we effectively are sort of looping, constantly looping through the driver function by invoking continuations. Okay, any questions about this at this moment? Okay. All right, cool. So that was just meant to be like a recap of what we talked about yesterday. I want to move on to how to actually implement continuations. Would you turn on the light again? Because I promise there won't be these color issues again. They'll be like normal slides. Okay, so so today's topic is how to implement. I guess we're having a light problem. It's fine. Is how to implement first-class continuations by source-to-source translation. It's based on this PLDI paper we wrote a couple of years ago. But like the meta topic that I want to really convey is sort of how to conduct research on like a full-fledged programming language, JavaScript here, like without losing your sanity. Okay, so let me sort of start. So before we get into like implementing continuations, let me start with the motivation of this paper that we wrote. So we started with the observation that there's several languages compiled to JavaScript. In fact, I can say something stronger than that. Just about any language that I can think of at this point compiles to like JavaScript because it's universal, web-based demos are cool, and compiling to JavaScript is easy. You know, caveats apply, but it's more or less easy. So there's a couple of compilers for languages that actually have interesting control operators. That animation got a little messed up. So for example, there's a compiler for Racket to JavaScript called WeScheme that fudges blocking I/O. The Dart to JavaScript compiler implements generators, and I believe they work on versions of JavaScript that don't support generators, so they sort of do something to fudge generators, which is effectively continuations. JS of OCaml is an OCaml compiler that, if I remember correctly, implements OCaml's notion of threading in JavaScript as well, using continuations. So there's like a whole bunch of compilers that effectively implement first-class continuations in JavaScript. So in some sense, this is nothing new. There's a whole lot of other compilers, however, which sort of just drop support for all the interesting control operators. So they take the source language that they're interested in compiling in, which is presumably better than JavaScript because, that's not hard to do. The language has a bunch of interesting control operators, and they just ignore them. They just rule out the control operators that don't directly translate to JavaScript in a straightforward way. All right. And that's unfortunate. So now there's a number of different ways of implementing first-class continuations. I'm going to cover like one of them in some detail, but just to like list a couple. Let's see. There's something called continuation passing style, which some of you may have heard of. There's what are the other approaches? There's sort of eager versus lazy approaches, and there's all sorts of like other sort of tweaks on well-known approaches. So, one question you could ask is like, what is the best way to implement continuations in your language when you're compiling to JavaScript? So this is a really hard question to answer. So first off, like any kind of like cross-language performance evaluation is just fraught with all sorts of problems. One of the things that makes implementing continuations really hard is that it sort of tends to pervade like pretty much all aspects of your compiler and runtime system. So if you decide tomorrow that, I'm going to switch from like CPS to this other approach, well, chances are you're rewriting a good portion of your compiler, maybe all of it. And that's just like not feasible to do. Other problems are that the actual answer, what is the best approach may be browser dependent. It may be that in one browser, let's say, implements tail calls really well, and sort of just doing straightforward CPS is the right way to go, and in another browser, that isn't the case. The answer may also be program dependent. So there's different approaches to implementing continuations, and some work better when your program, for whatever reason, is constantly capturing and restoring continuations. Others work better when, I mean, there's a cost to supporting continuations, and so others work better when continuation capture is relatively rare, and most of the time your program is not capturing continuations. Okay, so the answer, you know, to what's the best approach just sort of depends on a wide variety of factors. Okay, so so here's what our system, which we call Stopify, does. It adds first-class continuations to JavaScript, and this is different from prior work, which added first-class continuations in other languages and compiled them to JavaScript. So there's like a subtle difference here. We're both implementing continuations in JavaScript, but we sort of do that at the JavaScript level instead of for some other source language level. Small difference, but big impact. Basically, what we can do, so the other thing that Stopify does is using continuations, it implements a bunch of really nice abstractions. So you can stop and resume a running program. You can run a long computation on the main thread without like locking up your browser or getting like a frowny face in Chrome. You can, at a higher cost, you can implement breakpoints and single stepping through a program. We can fudge synchronous I/O, which we've seen already. We also support like web browser events, which is a somewhat trickier mess. This last point, Stopify also has polyfills for native higher order functions that support continuation capture. Let me explain that a little bit. So there's a bunch of like higher order functions in JavaScript that are built into the browser, map, filter, etc. These functions, they, well, because they're native, if you try to capture a continuation when, in the context of one of these functions, like in the argument to one of these functions, you're basically toast because you can't sort of do anything with that native stack frame. So you need to re-implement these higher order functions in JavaScript so that we can actually examine the continuation. So Stopify does all of that as well. And the basic idea is that we've done all this. So the right way to implement control operators now is you target not JavaScript, but JavaScript with support for first-class continuations, and then we'll take off all the dirty work of getting your control operators to work using continuations. So this is a really common kind of pitch, right? So we implement first-class continuations for JavaScript once and for all, and you don't have to do any language-specific stuff. So this kind of, it's an attractive pitch. It doesn't always work because it's often the case that language-specific solutions are faster, and you certainly want performance here. But there's results, we have results that suggest that our approach is actually competitive or faster than language-specific approaches. I'll get to the performance numbers later. There's a couple of tricks that we use to accomplish this. You could even call it cheating, but we'll get to that. But this, yeah, implementing something once and for all rarely works in practice because you can often sort of hand-tune an implementation for a particular language, but there's some cheats that we've pulled off here to make this work out, and we'll get to that. Any questions at this point about what we're trying to do? Okay. All right. So I just want to briefly mention how we're actually using Stopify right now. So we have this web-based programming environment that we use in a sophomore level programming course, where that's used by a couple hundred students a year and a couple of instructors. Basically, well, okay. So the goal of the course is not to teach web programming because you don't want to teach web programming to sophomores, in my opinion. We certainly don't want to expose students to like callbacks and all that other nonsense that you have to do to actually write web programs. So we use Stopify for like synchronous I/O, long computations to get that stop button to work without crashing the browser, etc. Okay. So here's the high-level idea of how Stopify implements continuations. Basically, what Stopify does is that it instruments every function in your program to run in 3 modes, right? So and the mode is like this global variable in the runtime system. So in normal mode, the function runs normally. In capture mode, the function like saves its own stack frame and returns to its caller, which does the same thing, right? So that's capturing a continuation. And in restore mode, we're actually trying to invoke a continuation. Here what the function does is it takes its own saved stack frame, restores its local variables, jumps to the point where the continuation was, and proceeds running. The Stopify has a runtime system that basically manages the transitions between all of these modes. And essentially all that the implementation of control does is that it's a function that sets the mode to capture. Okay, and applying a continuation sort of throws away the current stack by like throwing an exception and sets the mode to restore. All right. So at a high level, that's what this involves, right? So you're either running the program, or you're trying to capture a continuation, or you're trying to invoke a continuation. Those are the three modes of execution, and that's what Stopify manages for you. So I think the next 2 slides, I want to dig into this a little bit. Okay, so let's start by just talking through this function that does some continuation capture. We'll use this as a running example. Okay, so what are we doing? So we're calling the function f apply to 0. So here's f. So we print enter f. Then we apply g to x plus 10. So then we go into g, we print enter g. Then we, I guess the sum is pointless, whatever. So we call the control function, and what that does is capture the current continuation and pass it to save. And in saved, what we do is in the save function, what we do is we store the continuation in the saved variable. So since the continuation has been captured, at this point, the program sort of exits. So, okay, now if we were to apply the saved continuation down here, so let's say we did saved applied to some argument, let's say 0. Oh, so the plus wasn't pointless. Continuations are confusing. So if we applied the saved continuation to some argument, let's say 0, we would return here. We would end up doing y plus z. We'd return here, and then we'd log the result returned by g. So what's important is that when we invoke the continuation, we are effectively re-entering these functions, but we need to like jump over like that console.log and that console.log. It's important that we not re-invoke that stuff, because that stuff was executed in the past. The continuation is really what we're going to do in the future. Right? Is that clear? Any questions on this? If anything I said sounded like dicey, please ask. Okay, so so to introduce this, let's think about how we should represent the continuation value that gets captured here. Right, so like, what is the information that's required? Okay, I mean, basically, what we need to be able to do is reconstruct the calls to f and g without, printing over the console.log lines that were executed in the past. All right, so here's what we're going to do. Essentially, so I'm just going to like write down these labels here. Okay, so think of these as like abstract line numbers. One way to think about what the continuation needs to be is that it needs to be like an array of, these are like effectively stack frames, where each element of the array has the function that we were supposed to call, the line number that we were supposed to jump to, and the values of the local variables that are relevant. Okay, so the way to read this is that when we re-invoke the continuation that's saved, we first enter the function f with x as the value of, with 0 as the value of x. But what we do is we jump to line 5, skipping over the console.log. Then what we do is we enter the function g with 10 as the argument, and we jump to line 2, skipping over that console.log. And at that point, whatever the argument the continuation was applied to, that's the value that we use for z. Right? Is that a question or? Okay. Yeah.
Is that really
I'm sorry, would you say that again, please?
5 was like var s equals g of x plus 10 plus g of x plus 11.
I'm sorry, would you just go over that example again? I like tripped on this. So if line 5, oh, you mean that line 5?
If that was like g of x plus 10 plus g of x plus 11.
Oh, crap. Good question. Let's just ignore that problem for now. But I'll get to it in 2 slides. Right. But for this particular function, where we're not doing something like that, this works just fine. Right. So, any questions on this? I'm happy to just go over it again. Okay. All right. So intuitive. I mean, I've sort of explained this by pointing at the code, but intuitively, hopefully the intuitive explanation makes sense, right? So enter F, go to line 5. Oh, enter F with 0 for x, go to line 5. Enter G with 10 for y, go to line 2. That's basically what we do. Now, the question is how do you pull that off? All right. So let's just pretend that JavaScript has goto. Okay, that's going to make our lives a lot easier. Right, so goto, has anyone programmed with goto? I'm just curious. Who here has actually used goto in what programming language?
Lua.
Lua has goto, good to know. All right.
Same.
Well, there's that. Yeah, okay, great. Yeah. Basic? Has anyone actually used basic? Okay, cool. Yeah, so let's just pretend that JavaScript has goto. So you can say goto some line number and it works. So given goto, it's pretty straightforward to implement the restore logic. All that we need to do is add a little conditional at the top of each function that says if mode equals restore, then, so we have that array there, right? So restore the value of x from the array, from the first element of the array. We sort of, we store this label, so we read the line number that we're supposed to jump to out of that array. We remove the first element of the array. So let's see, how does this work? So in JavaScript, shift removes the first element of an array as opposed to pop, which removes the last element. Right? So we pop off that stack frame and then we go to L. So in that case, L is 5, so we go here. Same thing happens here. We read the value of y from the first element of the array. So at this point, we've popped off the first element. So the first element has the function g in it. So we restore the value 5, we pull out the label, we pop that frame off, we go to the line, which is L2, and we're done. So so let's talk about how to actually implement control. So control, well, it's a primitive operator conceptually, but we implement it as a function. Basically, when restoring a continuation, it's pretty straightforward. If we're in restore mode, we switch the mode to normal and just return whatever the value whatever value the continuation was applied to, right? So imagine that that's stored in a global variable somewhere in the runtime system. It doesn't have to actually be a global. Okay. Any questions on this? Right. We'll have to talk about what happens when we're actually capturing in a moment. Okay, so at this point we have JavaScript with gotos. Let's just ignore the gotos for a moment. Just pretend that that's okay. We'll get back to how we actually pull that off. Okay, so here's how we capture continuations. So to capture a continuation, the program has to save its stack. You can't one thing that you can't do in JavaScript is you can't sort of look at the stack and see what's on it. What you can do is you can throw an exception, and when you throw an exception, you pop a stack frame, pop a stack frame, pop a stack frame. And so essentially what we do is we instrument each function to catch these exceptions, save their own stack, and rethrow the exception. So there's a whole lot. So we're implementing continuations using exception handlers, which is a well understood strategy for doing this. Okay, so here's what that looks like. So I've sort of written ... for the restore mode logic. Essentially, around every function call, there's a little try catch. So what happens is that, well, actually, let's start by looking at control. So when we're doing normal execution, when the operator control is applied, what it does is it switches the mode to capturing, which I forgot to write down. So it switches the mode to capturing, and it throws an exception with 2 fields in it. In JavaScript, by the way, you can throw like random values. You can throw like 5 if you wanted to. So here I'm throwing an object with a field called stack, which is an empty array, and another field called receiver, which is the argument passed to control. So in this case, the receiver is safe. So what's going to happen here is that we're going to catch that exception, push the frame onto the stack. Oh, sorry, and another line of code missing. And then we're going to rethrow the exception. So pretend that this says throw exception. So that exception is going to get caught here. We're going to push this frame onto the stack that's stored in the exception and throw it again. All right, so that's continuation capture. Any questions at this point? Okay, so now let's talk about a slightly different example. And I think this is the last code example I want to go through. So this is a higher order function in JavaScript, right? So P takes f and g as arguments takes f, g, and x as arguments, and f and g are functions themselves, and it does g applied to x, and the result of that applied to f, and returns the value. So we can try to follow the same logic, right? So in restore mode, we do something, and then we number that line. We insert the try catch for the capturing logic, and out here we're going to push on a stack frame. So the problem is that this is not going to work. There's sort of 2 issues. So during capture, there's no easy way to determine if that exception was thrown by f or g, because we have this. Well, it would be really convenient if they were on separate lines, because then we just have a different catch block for each function call. But here, since they're on the same line, we can't tell which one threw the exception. The deeper problem is that during restore, go to L1 will always go here and will always call G first. But if it was F that threw the exception, well, we're basically screwed. Like, there's no way to sort of skip over the application to G. Okay, and this is related to the problem that you were describing. Okay, so here's what we're going to do. We're going to take that program there and rewrite it to this. Okay, so introduce a temporary variable t to name the result of g applied to x, and then we're going to return f applied to t. Does this look familiar to anyone from yesterday? Yeah.
It looks like a normal form.
Yeah, it's just a normal form, all right? This is just a normal form. It's literally a normal form. It's super helpful. So we use it to do this. I've used it in a bunch of other applications like program verification, type system design, program analysis. Reach for it first. It'll often help you. Would you agree with that? Yeah, great. Okay, so I want to now sort of give you a higher level view of like how we're pulling this off. So the first step before we do any of this instrumentation stuff is to translate JavaScript into a normal form. Oh, sorry. Okay, this is like the complete example. Okay, I'm sorry. There's another point that I wanted to make. So that's the program after a normalization. Here's the instrumented function. Okay, so when restoring, we restored the local variables f, g, and x from the stack frame, and then we go to the label L. And here's the try catch around the call to G. So if a exception is thrown to capture continuation inside G, then we push the stack frame onto the stack, and then we rethrow the exception. I forgot to write throw exception here again. So notice that I haven't written the try catch stuff around f applied to t. Okay, so people who know what tail calls are can probably see where this is going, but I just want to step through why it is okay to do this. All right, so So yes, so notice that in this instrumented function, we're not capturing and restoring. We don't have the capture restore logic around the application of f applied to t. Okay, so think about like what happens when we're inside f and f throws an exception to capture the continuation. So since we simply have return here, since we don't have an exception handler, what's going to happen is that whatever function called p is going to end up capturing that frame instead. Okay, so as we sort of build up the continuation value, there won't be an entry for the function p. Now, when restoring the continuation, so imagine that we're in the caller of p. So it restores its own frame, and then it effectively skips over the frame for p and immediately starts restoring the frame for f. And the reason that this is okay is because at this point, the frame for p is essentially useless. Right? All that it would have done is it would have taken the result that f produced and returned it. So it's okay if you skip it. So you can generate a more compact continuation value this way and end up restoring a smaller stack, like a shorter stack than what we had to begin with. And this is how we fudge proper tail calls in JavaScript. We periodically throw it. We periodically, once the stack gets deep enough, we capture the continuation and immediately restore it. And in the process of restoration, we end up skipping over the applications that were in tail position. Okay, so now a higher level view of like how we pull this off. Getting like normalization to work for JavaScript is like, I don't know, half the work. So it's like a, I think, 7-stage pipeline, possibly more. So basically, we desugar a few JavaScript features. What is the LaTeX error here? Oh, we add like curly braces around like loop bodies and the blocks and if statements. We eliminate all loops except while loops. We eliminate like the continue statement. We eliminate the switch statement, turning it into like if statements. Eliminate short-circuiting Boolean expressions. So for example, like that is annoying to have to think about. So that the function call to G is conditional based on the result of F, so we eliminate those things too. And at that point, we sort of do the heavy lifting of normalization. So once you've like eliminated all of this nonsense, normalization is like textbook. Right. So the reason that this works is that there's really straightforward assumptions and guarantees between each step. So when you're setting up this kind of pipeline, you have to think hard about like what what the requirements are and what you're ensuring for a subsequent step. So for example, this is like a LaTeX printing error, but like adding like a block around every loop body and every if and else block makes many of these passes simpler in a variety of ways. And the guiding principle for this was actually writing down a grammar for JavaScript in a normal form. So we like actually wrote it down. It's really short because there's sort of nothing to a normal form. It was like a 1 page in a Google Doc, and we knew that we were like driving towards that grammar. There's like only one optimization in this entire toolchain, which is that we don't anormalize expressions without applications. So like x plus 1, there's no function application there. There's no need to like anormalize it. So we'll get back to that later. And this is like a nice reusable artifact. So we like used it in another research project, and Emily's using it in something at the moment. Yeah.
Question. So in some cases, primitive JavaScript operators, for instance, when adding a string and an object together,
yes.
What happens is, for the object, the string method is invoked.
Yeah, we'll get to that.
How do you handle such cases?
I'll get to that.
Okay.
Yeah. Any other questions? Okay. All right. Okay. So that was, just to be clear, that was just anormalization. So the actual procedure is as follows. So we anormalize JavaScript. That's like 7+ steps. The second step we do is I think this is worth understanding. We box assignable variables that are captured by nested functions and may be captured in continuations. So let's not try to understand that. I want to show you another problem that occurs in compilers, and it's an analogous problem that happens here. So let's say I have a function f. So let's ignore continuations for a moment. Let's say you have a function f, and inside it you have a nested function g, okay, and we're returning g. So and what g does is that it does x plus y. So this is like the like the typical like make adder example. So we can name this result. We can apply f to 10 and get out a function add 10, and then do add 10 applied to 5. You can ask the question, like, is x on the stack at the point of this application? Right? And the answer is no, because we've sort of fallen out of f. So you need to do something. You need to implement closures correctly. And there's an analogous problem that happens when implementing continuations here. So if you have a assignable variable that's used in a nested function and it may get captured by a continuation, when you re-enter the function, you need to ensure that it's at the same, it basically has the same memory location. And you can't do that because variables have unique memory locations. So there's this sort of boxing step involved. It's something that it's something that doesn't occur in languages like ML, where there actually isn't any variable assignment and there's only mutable data structures. Okay, so goto. So it doesn't make sense to sort of implement goto in general. We implement something more limited, which is we only allow goto to the function applications within a function that we need to instrument. What gets tricky is sometimes, so what may happen is that you'll have a conditional, and you need to go to some function application that's inside a branch of the conditional, or like inside the body of a while loop, and enter that regardless of what the conditional evaluates to. It gets particularly weird when you capture a continuation inside an exception handler, and you need to jump into the catch block while skipping the try block. So there's a bunch of stuff that has to be gotten right here. I think the only real optimization that we have is that we avoid capturing code when it's obvious. When it's obvious that the called function will not capture its continuation, right? So we don't do that instrumentation when it's blindingly obvious. What does blindingly obvious mean? It means you're calling a function. It's first order, so you know what you're calling. You're sure that the function isn't reassigned to, and you look at that function and you see that it doesn't call anything else. I believe that that's the optimization that we have, and it improves performance by 30%. Okay. I had a lot of fun working with the student who was spending a lot of time on this. He'd keep coming up with increasingly sophisticated strategies for determining if a function doesn't call its continuation, and I'd enjoyed breaking it in various ways. So that was a lot of fun. I mean, really, to solve this problem well, you need program analysis, which we were not doing, but Anders will talk about later. Okay, so any questions so far? Everything that we've discussed at this point is JavaScript neutral. So everything that I've talked about, all the concepts will apply to any other programming language you may want to implement first-class continuations for. Yeah, go ahead.
Question: how did you deal with the enclosures? How did you deal with the enclosures?
Well, okay, so what can you do? So essentially, we end up inserting a bunch of conditional guards around each statement. You can do a little bit better than that by sort of coalescing statements that you don't need to go to, that you are sure you don't need to go to. But basically, what we do is that every function gets an additional local variable called called target. And in restore mode, what we do is we'll take a conditional and we'll sort of insert in a check to see whether the target is inside the conditional. So let me sort of write a really brief example. Actually, this doesn't really matter. Okay, so say we want to go to that function while restoring. What we do is we'll sort of say that this is target 1, and we'll set a local variable called target, and we say if mode equals restoring and target equals 1 or the existing conditional, and there'll be another, so I can't do this on the fly, but there'll be another guard around this to call the function if you're in restoring mode and the target is 1. And it gets tricky like when you have like a loop and things of that sort. But yeah, that's a good question. Anything else that I can answer? Yes.
I don't know if you mentioned already, but
Go ahead.
performance overhead?
I haven't gotten to numbers yet, but we'll go over them. So the answer is going to be it depends, and I'm going to give you like a long explanation. Right? Yeah.
Basically, to perform this notion, you have to call functions again.
I'm sorry. Would you say that again?
To perform the notion, you have to plan the function or call it. So otherwise, we wouldn't have the opportunity to go from the top to.
Yeah. We implement something really specialized, which is that you can only do goto while doing restoration while they're calling the function again. If I had to do this again, I think when we started doing this, we didn't realize that we were reinventing goto. If I had to do this again, I would have done like goto elimination as a completely distinct phase and sort of supported it in general. And I think it would have actually been easier to think about, though perhaps a little more work. Okay. All right. Any other questions? Yeah, go ahead.
In the end, so you started out with JavaScript, but after all of this translation, what's left is, you strip out of any JavaScript specific stuff, and what you're left with is a normal form, and
It's sort of idealized a-normal language, yeah.
so
To a large extent.
just as a remark, because in the end, in order to, so it seems that in order to implement first-class continuations or to do something useful with continuations, you have to strip out a lot in order to reason about that. Because, probably you could also, without all of these eliminations, you could also implement it in some way, but it's
Absolutely.
so freaking complicated or not feasible that in the end you end up translating it to lambda calculus.
Yeah, lambda calculus is like too extreme for just about any application. So wait, was that a question? I'm not sure.
No, I was just observing that in the end you eliminate a lot of what's inside of your language in order to get to the point where you can do something with continuations and you can restore.
Oh yeah, I don't actually want to think about JavaScript. Good lord.
Yeah.
No, I'll be less glib. Let's see. Why do things this way? Okay, it is certainly the case that it's possible that we would have gotten better performance by not being so aggressive about simplifying the language, right? So like, I'm pretty sure that turning all for loops into while loops is the wrong thing to do for performance. But I think, so there's a couple of goals here. So performance certainly is a goal, and we'll get to performance numbers. But there's other goals, like, you're building a research artifact. You want to be able to make progress, and this is the fastest way to make progress with a small group without, without losing your sanity. There's a couple of other random optimizations in here that we ended up doing that I don't remember anymore because I typically didn't do them. But this I really think that if you're like, especially in like a research group, if you're going to try to work with like a full-blown programming language, which in many cases is the right thing to do, these are the kinds of things that you need to do to manage the complexity. Whereas if there was a much larger team and we were extremely irritating. Like this is one of the things that you get out of using something like TypeScript. It tells you when you make these kinds of dumb mistakes, and you will make these kinds of dumb mistakes. So everything that I've told you so far happens to just work fine. I think just sort of a fluke in the presence of this behavior. So that's great. Okay, so here's the thing that doesn't really work. So it's not that these extra arguments sort of go up in smoke. Every function in JavaScript has this implicit argument called arguments, and it's an array, it's not really an array, of all the arguments. So you can write a function f here that takes and pass it in 4 arguments, and then we can iterate through the array of arguments and print all of them. And that works just fine. And an important detail is that this arguments array really has like all the arguments and not just the extra arguments. So if we like name one of them, argument 0 refers to x. So there's sort of 2 ways to get to that first argument. So this one actually prints.
So we print x, the first argument first. So that's the first one. And then we iterate through all the arguments, so we get
1, 2, 3, 4.
So this is a huge problem. Because if the function
is actually using the arguments object to do this kind of stuff, and we do what I've sort of told you before, all the extra arguments will get dropped. Like if what we do is we just sort of save the declared arguments in the stack frame, the extra arguments get dropped. Any questions about this behavior? Happy to answer like JavaScript trivia. I'm pretty good at that. Okay, so I want to show you I think one more thing. Okay, so this was brought up earlier. So here's a bit of JavaScript trivia. Can anyone give me a value for x that will make hello plus x go off into an infinite? Yeah?
If you define a string function that returns itself.
Yeah, and just to be clear, this is not a JavaScript specific issue. Like you have the same problem, and the same kind of behavior can occur in JavaScript, in Java as well. Right? So you can have x be an object with a toString method that has an infinite loop in it, which is crazy, of course. But that can happen. And so the problem that we run into if we want to actually support all of JavaScript is what if someone is stupid enough to actually capture a continuation in this toString method? Which is of course crazy, but it's something to have to think about and decide what to do with. Okay, so let's just talk about some solutions and what's wrong with them. Right? So the arity mismatch thing. So the obvious solution is don't save individual formal arguments. Instead, just save and restore the arguments object. So this is a huge performance problem. The arguments object is, it's mostly a bad idea in my opinion. And JavaScript jits go through a lot of work to make it not be a performance problem. So they try very hard to not materialize the arguments object as an array. So it's sort of conceptual array, and if every function call involved create an additional array, that would be bad news. So they do a lot of work to sort of not produce that array unless it's necessary. And if we start doing more stuff with it, we end up making JITs produce those arrays, which is bad. So the other problem is these implicit method calls. So it's pretty straightforward. All that we need to do is we need to make the implicit method calls explicit. So when you write something like this, we do x.toString. And it's actually way more complicated because there's also this value of method that JavaScript sometimes calls, and exactly what it does depends on a number of things. So this is bad because we end up with a whole lot of extra instrumentation. Remember, every function call means another exception handler, another sort of place that you can go to which involves more conditionals, yada yada. So this is also bad news. I think there's a final bit of bad news I want to talk about. So JavaScript supports getters and setters. So when you write something like this, like o.b, that can actually call the getter method. So that could also be a function call. And so I guess we could make the implicit call here explicit again. Again, it's bad because more instrumentation. This is all bad news. Okay, so this is a JavaScript specific problem slide. This is all just terrible. So yeah, okay, so here's what we do. Sometimes you can sort of get away with just ignoring all these problems. So back to what we're trying to do with Shopify, right? So we are the motivation for the work was you're compiling some other source language to JavaScript, and you have interesting control operators, and you want to get some of these things like blocking I/O, long-running programs for free. You can use Shopify to do that instead. So what we did to evaluate Shopify is that we took a bunch of existing compilers. I think with this 10 here, 9 of them are like compilers that other people wrote that produce JavaScript. We ran them, and then we ran Shopify on the JavaScript that they output. Now, let's see, how do I want to explain this? Okay, think of it this way. So, if you are compiling, okay, how about this one? So, BubbleScript is an OCaml to JavaScript compiler. So, if you're compiling a language as beautiful and pristine as OCaml to JavaScript, like, do you need all those crazy features? No, right? It turns out that if you can assume that the source, that the JavaScript that you're getting is the output of the BubbleScript OCaml to JavaScript compiler, you don't need to insert in all of that instrumentation. And that's basically what we do. So we support all of that stuff. It's actually not hard to do. It's just irritating. And there's a bunch of like flags to the Shopify compiler that you can use to enable or disable support for all of those various thorny features that I talked about. And that's sort of summarized here. So I guess OCaml is like the only one that's sort of pristine. Let's see, what else do we have here? So some of these languages, so there's like additional subtleties here that I'm not going to get into. There's sort of intermediate modes that we sort of identified, but basically any compiler that compiles into JavaScript typically doesn't use all of the languages features. It uses some subset, some sub-language of JavaScript. And basically what we did in Shopify is that we identified some of these sub-languages. We even found that, it's kind of unsurprising that a number of compilers sort of share the same sub-language accidentally, and that's what we sort of target and specialize for. In fact, the only source language that requires all features is like JavaScript itself. All right. Any questions at this point? Okay. So we'll get to like numbers now. So like once you do this, you identify the right sub language, you can improve performance dramatically. So just an example with Python to begin with. Let's see, what do we have here? So on the x-axis, we have a bunch of Python benchmarks that we were able to run through the PyJS, Python to JS compiler. And on the y-axis, we have the slowdown relative to PyJS without Shopify. Okay, so like 1 means we're running as fast as PyJS, above 1 means, so this means that we're 10 times slower. So if we run Shopify in a mode where we instrument all operators to support these implicit method calls, we get pretty terrible performance. Like 10x here, more than 30x there. But it turns out, with some, by sort of looking a little bit at the code generator in the PyJS compiler and looking at some examples of code that it produces, PyJS doesn't actually require implicit method calls. So, add that as a flag and you get vastly better performance across the board. So this is something, I guess this is something that I didn't pay at least too much over. This is making a different, this is something that I didn't really get into earlier. So, it turns out in JavaScript there's 2 ways of calling functions. You can sort of call them normally, and the other way you can use them is as constructors. You can call them with new. And there's 2 different ways of implementing continuation capture and constructors that we came up with. And the performance, you get sort of different performance in different browsers. So this graph compares like Chrome and Edge. So we call the 2 techniques desugaring and dynamic. And what is this showing? Okay, so I guess it's showing that. How can I summarize this? Okay, it looks like the dynamic approach is faster the desugaring approach is faster on Chrome. So, I mean, that's not going to matter very much shortly, but this was true 2 years ago. Yeah? Yes. Yes. Yeah. So both of, I mean, all these bars involve PyJS plus Stopify, and the baseline one means is we're running at the same speed as we're running at the same speed as PyJS without Stopify. There's a couple of like flukes here. So in some cases we actually are faster than PyJS, and that's just like a fluke. PyJS does some really terrible code generation that uses features of JavaScript that nobody should use. And we end up accidentally eliminating those features at some point in our sort of simplification, in normalization pipeline. And so things happen to go faster. But that's, I wouldn't read too much into that. OK. So let me, here, I'm going to zoom in. So, so we evaluated Stopify on 10, so I'm going to start with 9. On 9 third-party compilers, and the approach was take a compiler, run the benchmark through it, run the program through the compiler, get JavaScript, run that program through Stopify with a various flag set, and the flags were a couple of slides ago. We ran it on a bunch of different platforms. So let me zoom into like one of them. Let's, how about Scala? Okay, apparently I can't zoom into. Okay, not JavaScript, because that's boring. Okay, here's OCaml. Okay, what happened? All right. So this is. Let me make sure I'm talking about the right one. All right. Yeah, this is OCaml. Okay, so this is what's called a CDF, a cumulative density function of our experiment. So here's how you interpret the graph. So each line is for a different platform. So we ran it on all the four major platforms, and we threw in a piece of shit Chromebook because part of the motivation is we want like students to be able to use this on an inexpensive hardware. So the median slowdown, I believe this is the median slowdown, is what's in parentheses. So you can see that on average, the slowdown of OCaml using the buckle-strip compiler is 4x on Safari and up to almost 9x on Firefox. But the CDF gives you a little bit more information. So the way you interpret this is we have slowdown on the x-axis, and the way to interpret the y-axis is the fraction of benchmarks with slowdown less than whatever we have on the x-axis. So for example, so this is 10. So roughly speaking, let's take the Safari line, which is red. So this means roughly 75% of the benchmarks have slowdown less than 10x. Right? And then we sort of start trailing off, and there's a long tail of certain things have a slowdown of up to 40x, which is actually it sort of levels up here. So I think on edge, the slowdown, I mean, there's some really bad outliers on edge, but all of these ones sort of level off here. Any, yeah.
Do you know why Firefox is also?
No. Yeah. Okay. So no, I do know. So you should not interpret Firefox being slower as Firefox is slower. So like the students and I building the system, we did all our development on Safari and Chrome, and benchmarking it on Edge and Firefox was just an afterthought. So this does not mean that Firefox is slower, it just means that we didn't try. So I wouldn't read too much into that. But good question. Thanks for asking. Yeah?
I mean, you use a lot to PlayStation and I mean, while I was reading this picture, because I read the paper, and I concluded that JavaScript has the biggest slowdown.
Oh yeah, it does.
On all 9.
Yeah, but I mean, it's sort of. Yeah, so here's like the never mind the CDF. Here are the mean slowdowns on JavaScript. I mean, really, what it's telling us is that to support JavaScript, to support the JavaScript benchmarks, and we ran some pretty old benchmarks here, if I remember correctly, you need support for all of those crazy features. And when you do, yeah, of course, the slowdown is terrible. I mean, these slowdowns correlate strongly with like which flags we needed, which features of JavaScript we needed to support, like which sublanguage of JavaScript we needed to support. So OCaml was pretty good because it just uses like the core of features of JavaScript and doesn't use any of the crazy features. Was there another question there? Or? Okay. Right. Any other questions about this? We can like zoom in on, your favorite programming language if you like. These also correspond to like how much code each compiler generates. So like Scala.js is very faithful to Scala, and it actually turns the whole standard library into JavaScript and doesn't sort of, it doesn't usually, so for example, when a benchmark uses a Scala list, it doesn't sort of translate it into JavaScript arrays. It just sort of creates like the list class, etc. itself. So Scala.js generates an enormous amount of code, and so this performance is mesh on Scala. So I wouldn't, yeah, so there's a number of factors at play that determine what the slowdown is. So, I mean, this is not super helpful, right? Because, okay, the slowdown is, the slowdowns are like all over the place. It's hard to tell like what slowdown is acceptable. So, we're getting something out of this, right? So we're getting support for blocking I/O, long-running computation, stop button, etc. It's going to come at a cost. What cost is acceptable? And you can't really, I mean, 50x is bad, but other than that, you can't really sort of tell that from here. So what we did, so to do a more useful comparison, though this is difficult to do, we compared PyJS plus Shopify with an existing system called Sculpt, which implements Python in JavaScript and does this execution control stuff. So it's used by like a number of these like online coding platforms to create like a Python IDE in the browser. So now there's a couple of issues with this comparison. So first, it turns out that Sculpt is pretty broken. It can only run like 8 out of the 16 benchmarks. And if you dig into this more deeply, like you throw like the CPython test suite at PyJS and Sculpt, they end up passing and failing different subsets of the test suite. So they're not really implementing the same language. So, there's like many other possible threats to validity to this comparison. So take this with a huge grain of salt. But here's what we get. So these are the benchmarks that we managed to get both Sculpt and PyJS running on. PyJS plus Shopify can run more benchmarks. This is the mean slowdown. So, we're a little slower on that benchmark, but we're actually faster on most of them. So, given that this is faster than something that people already use, that suggests that at least for the application that this is designed for, which is sort of teaching programming, this is a reasonable solution. Right, any questions on this? Yeah.
So this is Shopify, like Shopify on Sculpt, or?
No, it's Shopify plus PyJS versus Sculpt. Okay. So yeah, so it's a really big grain of salt required, right? So it's not the same compiler with and without Shopify. To do a comparison to do Shopify plus Sculpt versus Sculpt plus its own execution control, we would need to like go through the effort of like deleting the execution stuff, the control stuff in Sculpt and sort of retrofitting Shopify on top of it, which was not feasible. Well, it was like very close to feasible at the time. So Sculpt has some mode where it doesn't generate its execution control stuff, if I recall correctly, but it made heavy use of eval to like dynamically generate code, which at the time we didn't know how to deal with well. At this point, Shopify has really good support for, like you can call eval and it sort of does, and it doesn't sort of crash and burn. It does the right thing in the presence of eval, which you need to implement like a REPL in the browser. So we could sort of redo this experiment, but we were not, at the time, that direct approach wouldn't have worked. We would have had to become really familiar with the Sculpt code base, which we were not interested in doing. Yeah. Yeah.
How do you deal with eval if you have continuations, like control inside an eval?
Okay. Well, okay. I mean, basically, you need the Stopify compiler available during runtime, which is what you need to do to implement eval anyway. Okay. So we start from that. It's actually really straightforward in some sense. We roughly speaking, you instead of calling in the built-in eval, you call our Stopify eval. You instrument the code in place and then start running it, and it sort of works. But the only thing you really have to get right is you have to get the global environment right, which is the normal problem with implementing eval. Like it's a global variables are like have to be like a dictionary because you may introduce new global variables. But it's not like a sort of unique problem to this. Sorry for moving. Any other questions here? Okay, so to do a more reasonable comparison, what happened to mine? We decided to apply Stopify to a programming language called Pirate. I'm just curious, who's here has heard of Pirate? Anyone? Just a couple of hands. Okay, so Pirate. So I should start by saying that Joe Politz, who's one of the lead developers of Pirate, was a co-author on this work. So we had someone who was like actually intimately familiar with this compiler, which let us get into the guts of it. So Pirate is this mostly functional programming language that compiles to JavaScript. It has a self-hosting compiler. You know, it really inspired this work. So it does a lot of what we do in Stopify. So proper tail calls, blocking I/O, REPL animations, you know, graceful stop button that you can click on the stop button. The program terminates normally without crashing your IDE. This is built by sort of Joe and others. At the time, they'd put in like 5 years of engineering effort into it. They have thousands of users, and it still had some issues. So basically, what we do is we modified the last phase of the Pirate compiler and portions of the runtime system to invoke Stopify instead of doing the capture restore logic that they had baked in that was Pirate specific, and basically ended up deleting like a lot of code in the process. So I just want to give you a sense of what that looked like. So here's some code from the Pirate runtime system that implements a for loop, iterating over a range. So what this function does is that given a start index and a stop index, it applies the function fun for all values in that range. And that's the implementation. Basically, it deals with the problem of what if this function needs to be suspended for the purposes of keeping the browser responsive while we're inside the for loop. It's handwritten in JavaScript for performance reasons, and there's just a bunch of like sort of make cont and whatnot, continuation management nonsense around this. And I should say that applying Stopify this way, where you're intimately familiar with the compiler, is the right way to use a tool like this. Right? Blindly applying it to the output of some compiler that you don't understand is not the right approach. Yeah? 5 minutes? Okay. So once we use Stopify, the implementation turned into that, which is the obvious way to implement this function. Okay, so here's another CDF of the performance on Pirate. So let's start with the means that are, I think these are medians that are in the legend. So the slowdown is about 1.1 on Safari, Chromebook, Chrome. We do worse on Firefox and Edge. Again, I don't think it's because these browsers are slow. It's because we just didn't explicitly performance tune for them. So once you actually look at the CDF, they tell a different story. So there's like a long tail of benchmarks on which we get terrible performance, like 40x slowdown versus Pirate. And all of these benchmarks, so we looked into them. Pirate implements proper tail calls and supports an unbounded stack. So it's impossible to get a Stack Overflow exception in Pirate. We do that too, but we do it worse, and we just didn't pay much attention to it. And we're confident that we can make this better, though we hadn't gotten around to it at the time. Okay, so the long tail of really slow benchmarks are things that repeatedly that really sort of push the limits of how big the stack is. Any questions on this? Okay, so think this is my last slide, yeah. So I just want to sort of give you some sort of concluding thoughts on like how we pull this off. So I think one of the most important lessons is to like use existing infrastructure when possible. So Stopify is built on top of a sort of JavaScript transformation toolchain called Babel that's really great, and that's what we use for like all of this. The main lesson though is when you're working on a full-scale language such as JavaScript, you really need to like identify like the small fragment of the language in which like the essence of the problem and solution that you're after can be formulated, and then sort of grow out from there. So don't, it's a big language, find the small language in there that really matters, and then grow out so that you can actually run real benchmarks, etc. The actual translation that you end up using is likely to be problem dependent. So I've worked on JavaScript in the past doing other kinds of things with it. So for example, type checking. And when you're doing that, the translation is subtly different in certain ways. Like I of course use ANF because what else would I use? But there's different kinds of tweaks to the core transformation that you need. Yeah, using ANF is likely to help you. And when you're actually working at the scale, you need to think hard about like testing and CI, and that's like another kind of talk that I can give. All right. So that's all from me. If we have a minute or two for questions, yeah, happy to take them.
Do we have questions, Arjun?
I can't see anybody.
Yeah, I can see lights, but this is complicated.
That's okay. Yeah, go ahead.
So, continuations don't make sense.
Okay, that they should.
I've made a language.
Yeah.
I always wonder how far we expect people to go forward with being able to use them for anything beyond a few simple cases. What insights have you got that comes to people who can actually use this? Obviously, you've got much further depth of this than most people.
So you mean use it to build new control operators? Well, I think we're familiar with a lot of the sort of most useful applications. They're sort of well understood. While you can do a lot with them, not everything actually needs full-blown continuation. So I'll admit that. So for example, I talked about generators. You don't need full-blown continuations and to implement generators as they exist in most programming languages. But there are certain applications that really do. So here in particular, where we're using continuations to sort of simulate blocking I/O, you really do need full-blown continuations. What else are we doing here? So like the example that I gave where we were doing probabilistic, well, I gave an example of non-determinism, of implementing non-determinism. I think doing that in other ways, like in monadic style, in my opinion, is harder, and it works more naturally here. So yeah, I mean, they're a really powerful hammer. The thing with powerful tools is you want to avoid using them as much as possible, right? I mean, they're in the class of things like macros and eval. Like if you think you need to use them, think really, really hard before you use them. So, but they're a good tool to have in your toolbox for, when you really need them.
Thank you. Is there any other questions, Arjun?
All right.